And all I did was I substituted the gradient vector of f for our function, which is dependent on v. And v, we're told, is the electrical potential. So they want us to find the rate of change of the potential at a particular point. So the first thing we want to do is that we want to normalize the unit vector, which is this unit vector. It's also, let's make this a little bit bigger. And this unit vector is given by v equals I plus j and negative k, which we got it right here, is in the form in just a different notation. And so to come up with the unit vector, basically we want to divide by the magnitude of the vector. So we take all of the components, and the magnitude again is just the square root of the sum of the squares, which gives us square root of 3. And so this right here becomes our unit vector. You could also distribute the 1 divided by root of 3, or you could leave it outside. So we're given the function of the potential difference, electrical potential, not potential difference. And here, here's the equation. Let me highlight it. So v of x comma y comma z equals 5x squared minus 3xy plus xyz. So then we want to construct our gradient vector, which in this case it's accomplished by taking the partial derivative of the function v, and first we do it with respect to x, then with respect to y, and then with respect to z. And again, partial derivatives are rather simple. We just in again chapter 12. Actually, no, that was actually chapter 14. Chapter 14.3, partial derivatives. We learned how to take partial derivatives. So once we take the partial derivatives, we want to put the vector, the gradient vector, in this notation, and then we want to take the dot product, or in this case, we want to, because we're asked to find the rate of change of the potential at a point P. So the point P, we evaluate the point P once we have our gradient vector constructed, and this is our gradient vector at that particular point. So once we have the gradient vector evaluated at the given point, we want to go ahead and take, sorry, that was not the pen I was looking for. We want to go ahead and take the dot product of the gradient vector and the unit vector, which again we calculated at the beginning of the problem, which is this unit vector right here. And the dot product was covered in section 12.3, I believe. Yeah, so we did cover the dot product on section 12.3, but it's very easy. All we have to do is take just gotta multiply each component of the vector. So the I component with the I component of this vector right here. And then the j component with the j component, and the k component with the k component. We add them up algebraically, and then our result is 32 divided by a square root of 3. And this number here, it's a scalar, and it represents the rate of change of v in the direction of v, actually v at the point p. Point is 3, 4, 5. 3, 4, 3, 4, 5 in the direction of u. In the direction of u. And just a note on units. If we had, if the problem would have assigned any units for this vector v right here, where if they would have said that the region was measured in meters, for instance, then our rate of change would be in volts per meter, and this would be consistent with the units for the electric field, which is consistent with the definition from physics that that by taking the partial derivative of the electric potential, we get the electric field, and vice versa. If we take the integral of the electric field, we get the electric potential. Part B, we're asked to calculate in which direction does V change most rapidly at P. So here we have, again, our equation for the electric potential, and then we want to use the same directional derivative formula. So again, del f is this part right here, which it has the partial derivative of the function with respect to x, with respect to y, and then with respect to z, and then the dot product again against the this unit vector u. So if we want to know where is the potential, the gradient vector maximized, we want to take a dot product where this angle right here is equal to 0, because cosine of 0 equals 1. So that is the direction in which the potential will be changing most rapidly. So again, we take the partial derivatives, and then we calculate the point P, and the results for that are, when we take the partial derivatives of the function with respect to x, we get, and then we evaluate the point, we get that it's equal to 38, and then we take the partial derivative with respect to y, and then we evaluate the point, and then we get that is equal to 6, and then at last we take the partial derivative of the function with respect to z, and then we evaluate the point, and we get that it's 12. So our potential function will be changing most rapidly at the point P, where with coordinates 38, 6, 12. And then for part C, we want to know what is the maximum rate of increase at the point P. Here, I want to show theorem 15. And theorem 15 basically says that the maximum value for the directional derivative is it's the magnitude of the gradient vector of the function and the cosine of the angle. So again, as we did in B, this will be maximized when the angle between a u and f is 0, and this happens to be the same direction when U has the same direction as the gradient vector. So since we already know what is the direction of that gradient vector, all we have to do is take the magnitude of the gradient vector for the potential, which is this right here, and our gradient vector, of course, is at the point P is 38, 6, 12, and then taking the magnitude gives us a value of 2 root of 406.